So today I'm going to present our new congestion control algorithm called Mutant that learns from existing protocol via online reinforcement learning. So as we all know, congestion control is one of the most challenging but also active research areas in the networking community. And years of congestion control have proposed a large amount of work that all share a common goal. They all wanted to propose high bandwidth utilization protocols and to achieve a high throughput, low delays, and also reliability to deal with complex network conditions. And also they want to achieve fairness and fast convergence to fairness. However, we observed a recurrent pattern in the congestion control design, specifically the design cycle that we have seen so far, and that we observed is the following. Researchers would look for the state of our congestion control algorithms and where they actually fail, and in order to improve them and tailor this new algorithmic design to their needs and to their specific network conditions. A new design then comes out after intense experimentation and evaluation until a new researchers or new designers will make it fail in new scenarios where the original proposal hasn't been designed for. So we need to repeat this process over and over to fill this new gap. Well, this overall process is wrong for many reasons, but above everything is time consuming because it needs time to design, implement, also experiment a new congestion control algorithm, and for these reasons it's not sustainable in the long term. This design led to development of a set of different congestion control algorithms in the recent years that always fail in some scenarios. For example, here we just compared popular traditional congestion control algorithms such as Cubic, Hybla, BBR, and Vegas in terms of the ratio between throughput and delay, and tested on different network scenarios. And they all perform very differently according to the specific network conditions. For example, BBR developed by Google can perform very differently considering the network scenario it is tested on. The good news out of this story is that all these protocols can perform really well in the set of scenarios, network scenarios that have been designed for, which is something we can take advantage of. So in this work, we propose a new design which takes advantage of years of research and experience in the congestion control area by automating the design cycle that we've seen previously and formulate a new congestion control algorithm and mechanism that learns from the existing congestion control schemes instead of proposing a new one that is based on their drawbacks. So the research question that we're posing is the following. Can we build a learner effectively from a pool of existing protocols without involving an impractical data collection, which would include a training offline, for example, of a huge static amount of data, but also without optimize this new protocol to work for every possible network condition, but instead make it adapt dynamically to new ones? So we designed Mutant, an online reinforcement learning algorithm that learns from existing in-kernel congestion control protocols. So Mutant system lives in both kernel and a user space of a sender host, and we co-designed Mutant as a two-part module. The first component runs in the Linux TCP network stack, while the other, the learner, runs in the user space. So on a high level, Mutant runs a reinforcement learning agent that predicts the next congestion control protocol to run in the near future based on real-time network conditions. In order to do that, for a specific network scenario, we developed an algorithm that is called Mutant Protocol Team Selection that would select the best K protocols out of the pool of congestion control schemes in the kernel. Once the pool of protocols has been selected, then for that specific network scenario, the user space and the kernel space, so the two components that for Mutant would interact and communicate each other to predict the next congestion control to select in the very next time step based on real-time network statistics that are collected in the kernel. And so this is an example of a Mutant client, a running Mutant client. So overall, Mutant system comprises of the learning module in the user space, which includes the reinforcement learning agent that predicts the next protocol, so the action of the reinforcement learning algorithm, and the protocol manager that runs in the kernel as a pluggable custom module, which dynamically switches the underlying protocols in real time and smoothly handles the individual protocol state variables in order to be saved between each swap. So next, I'm going to introduce the protocol manager a little bit more in details. The protocol manager is designed using the same format as a custom TCP congestion control algorithm that runs in the kernel. It is also designed to store all protocol state variables, and we did this in order to maintain a memory of the evolution of each protocol the moment they are swapped with another one. And then it collects the network statistics in the real time to send them over the learning agent in the user space, using a NetLink socket interface. So this component essentially acts as a meta protocol in the kernel. So it runs a data structure. It runs actually two main data structures that allow this component to perform the live switching behavior. These two data structures are the following. The first one is a set of function called pointers that point to the actual TCP event-specific functions of the existing congestion control schemes. Examples are the update of the congestion window, or the receiving of an ACK packet, or again, the trigger of the congestion avoidance mechanism. The second important data structure that this component owns is a global data structure that will serve as a wrapper for referring to the protocol-specific state variables. Examples are the congestion window or specific parameters of the congestion control protocol. So together, these two data structures and the overall interface that we implemented allows this component to perform this plug-in, plug-out mechanism and to achieve the live switching behavior between different protocols in the kernel. Upon receiving an ACK, so this module will communicate the network statistics collected over time and send them over the learning agent that would return the next action, so the next protocol to be predicted for the next time step. So the new congestion control scheme will be loaded, and it will run for a predefined amount of time. Then I'll introduce the learning module. This component hosts the online learning capabilities using a reinforcement learning agent, and the agent will perform an action, so the next protocol to be selected based on the state, the network conditions, in order to maximize a reward over time. For the reward, we define our reward as the ratio between the throughput and the RTT, the delay actually. So because we want to maximize the throughput, but also minimize the delay at the same time. To predict the next action, the agent will use a policy, which will learn the relationship between the context features and the expected reward of each action. That would be, of course, each protocol of Mutant's kernel. As a policy, as overall reinforcement learning algorithm, we use a contextual multi-arm bandit. We had two challenges that we had to deal with during the design of the online learner. The first challenge is the exploitation trade-off, which is a common challenge in the reinforcement learning field. So where exploration means that we want to select different actions in order to to gather more information about the environment, regardless the performance of the individual actions. Exploitation, meaning we're gonna select actions to maximize the reward in the short term with the known information about the environment. The second challenge instead is reducing the input representation, because we have overhead constraints as a congestion control algorithm. So we want the network features to be as small as possible in terms of the size of the input. So for the first challenge, our goals are minimizing the exploration time, but at the same time also building an online learning process that would be as fast as possible, and maximizing the reward over time. To achieving all these goals simultaneously, we propose a simplification of the traditional reinforcement learning using a linear upper confidence bound policy in our reinforcement learning agent. The linear UCB assumes a linear relationship between the expected reward of an arm, that would be the action of our reinforcement learning system, and the contextual information. So the policy models the relationship between the contextual feature and the expected reward for each action using the Bayesian linear regression to estimate the weights of the contextual features. The feature weights are then updated over time based on the observation collected in real time, in particular the reward that is collected, which is the core learning process. And then eventually it will compute the expected reward for that action, but along with the expected reward, our policy will also compute the upper confidence bound that represents the uncertainty of the estimate. So the range of values for the expected reward for each action is expected to shrink as the policy learns how to predict the next action. And for the second challenge, we reduce the input representation by means of an encoder network. And this encoder architecture is designed with 2 fully connected layers and 1 gated recurring unit. We use the GRU layer for its well-known capabilities in extracting sequence-level information. And for this reason, our encoder will be able to extract this sequence-level information from the context and reduce its input size by embedding the context features in low-dimensional vectors that will be used as input of our reinforcement learning agent. So we tested Mutant on real network conditions to emulate cellular links and a combination of different emulated wire network scenarios by tweaking some of the network parameters, like bandwidth or RTT and buffer queue size. We use Pantheon testbed and MyMy emulator to perform our experiments and hyper sessions to generate traffic. As baselines, we compare Mutant with a diverse set of baselines that we divided into 4 categories, end-to-end TCP designs. So there will be like the congestion control schemes that Mutant learns from. So actually the existing congestion control algorithms in the kernel, such as Cubic or BBR, Vegas, and Hybla, and so on. So and end-to-end cellular, such as C2C, TCP, or Sprout. Machine learning-based systems, congestion control algorithms that have been recently proposed, such as Indigo, Orca, or Sage, and mixed schemes such as LEDBUT. Then we configure Mutant using a maximum number of protocol of 6 and a switching rate of 10 milliseconds. But you can find more details on the configuration settings on the paper, of course. So in these figures, we present how Mutant performs in terms of how we can control actually the sending rate in order to achieve a high link utilization compared, for example, to a well-known congestion control protocol such as Cubic, which struggles to find the right sending rate. And here we can see how Mutant selects actually the best case settings and quickly adapts to changing network conditions. Then we compare Mutant with the in-kernel congestion control protocols that are present in the pool, which are the congestion control algorithms Mutant learns from. Here in these figures, for example, we can see how Mutant performs compared to this set of protocols in different cellular scenarios, network scenarios, in particular real 5G high bandwidth cellular traces. And the results show how Mutant performed consistently among the best congestion control scheme in the pool. Again, we repeated these experiments with emulated network scenarios. So we tweaked some of the network parameters, and we have different scenarios such as a low bandwidth or a large buffer queue and a high RTT network scenarios. And again, Mutant can still perform consistently with high level performance although it learns from these protocols that are present in the pool of Mutant kernel, it can still outperform them by learning its own policy over time, and thanks also to the finer granularity of its live protocol switching. Then we compare Mutant with a state-of-the-art congestion control algorithm recently proposed, including also machine learning-based algorithms such as ORCA, Enthalpy, and SAGE. In this case, we performed this experiment as in real-world network scenarios by means of the Fabric testbed. So we were able to reserve machines across the United States and Europe to perform intracontinental and intercontinental experiments. And Mutant consistently achieves high performance level in terms of the throughput and the delay. And what is surprising is that Mutant can match or even outperform machine learning-based congestion control algorithms that have been pre-trained previously on these network scenarios. I will conclude this talk. So again, we propose Mutant, a congestion control protocol that learns from a pool of existing congestion control schemes in an online fashion. We build an online reinforcement learning algorithm that can rapidly evolve and mutate into the best performing congestion control strategy out of a pool of selected protocols. We also design a lightweight, extensible in-kernel component that will perform the live switching behavior between different congestion control algorithms. And researchers can also try to plug in their own congestion control design as long as it can be designed inside the kernel. Our results also show that Mutant can achieve consistently high throughput and low delay on different network scenarios and compared to different baselines, including also a recently proposed machine learning-based system. Thank you, everyone, for your attention, and I'm happy to take questions.